So our next paper is on the design improvement of hybrid composite joints by Axiomatic Design. Our presenter is Aurelian Vadim from the Department of Mechanical Engineering at Polytechnique de Montreal in Quebec, Canada. And so, again, we'll have about 15 minutes of presentation.
Thank you very much. Okay. Thank you very much, Toby. Hello, everybody. I'm Aurelian Vadim, as Toby said, from École Polytechnique of Montreal. I have the pleasure to present the work that I've done with my student, Mark Ouellet, a master's student. So we studied the hybrid joints, which is a part of a bigger project now, a project where several industrial partners are involved. Bombardier, Dallas Tech. We have some university partners as McGill University, Carleton University. So it's a subject that is very important for the aeronautic industry. So just to give you an outline, I will talk about the context, rationale, couple of conclusions from literature, behavior, general behavior of a hybrid joint, the application of axiomatic design methodology, the physical integration of a new concept, and some comparison that we have made. Finally, conclusion. So, why we are interested in doing this? Because certification of primary structures in aeronautic do not allow yet bounded assembly. So we have to put always a bounded assembly. Why? Because it's difficult to inspect, and traditionally we have made the aeronautical structures in aluminum, generally in metal. So what is a hybrid joint? So you can see here a hybrid joint is a joint which allows to join two plates with a bolt, and we can have also bounded areas. A joint design can be viewed from different perspectives as a bounded substrates where we can add some bolts, or we can think totally new design, directly a hybrid joint, in order to have an optimum behavior. So, a little bit of rationale, what's happening in a hybrid joint. As you may see, we have here two plates, a bolt and a bounded area. The neutral axes present an offset. So when a hybrid joint is deformed, we can see here a kind of secondary bending induced by the tension applied to the plates. In terms of stress, we can yield here a shear stress in the bounded areas, in the adhesive, shear stress and peel stress. Peel stress, it's the normal stress that has the tendency to open up the joint. And of course, when we have a contact between the bolt shank and the hole, a bearing stress is developed. So this whole behavior we have to know it very well before proposing a new concept of a hybrid joint. What about the stresses? Because we are interested every time in evaluate the failure modes. So you can see here the peel stress and the shear stress, the major stresses that appears in a hybrid joint. The peel stress being the most important for the failure perspective, and the shear stress, the mechanism of transfer of the loading inside the hybrid joint. A little literature review, Hart and Smith. I give you some results because, of course, that there's a lot of literature outside. told that 19% of external load is transferred by the adhesive, but adding bolts can contribute to limit the crack propagation after initial failure of the adhesive. Chan told that bearing stress is rather low, and a failure based on these types of stress is unlikely. Kelly shows once again that we can take advantage of bolting on an adhesive joint, and we can take advantage of the preload that we install in a bolt to increase the performance of this joint. So, knowing a little bit what's about a hybrid joint, we proposed a new design concept for hybrid joints, and we tried to make a design not by adding bolts to a bonded joint, but to think about directly a hybrid optimal joint. Of course, before that, we have to know exactly what's happening inside, the interaction between different parameters, what we can propose as a solution for the different function that a hybrid joint may have. Of course, that beside we have developed a lot of tools, advanced finite elements, 3D finite elements, contact stress, contact elements inside the hybrid joint, analytical model to build a surrogate model which allows to rapidly assess the behavior from different parameters. So we have made finally a sensitivity study based on DOE plan. Here you can see a hybrid joint, 2-row bolting, and the parameters that we've studied. Why 2-row bolting? Because there's a lot of results available outside. So, what we evaluate, as you may see, the joint stiffness, very important, the bolt load transfer. What's the amount of loading that is transferred through the bolts besides the adhesive area? We have here, sorry, there's still some words in French. So the clearance, you may see here the substrate, the adhesive, the distance between bolts, and so on. The peel stress, once again, and the shear stress, the principal failure modes. And finally, the axiomatic design. What we focus on was identify the needs of a hybrid joint, needs as a customer needs for a hybrid joint, and one of the main objectives is to reduce the main failure mechanism, principally the peel stress. So we developed a new hybrid joint concept that we compared finally with a traditionally joint. So we use axiomatic design, we do the matrix decomposition, and finally a physical integration. So the zero level of our axiomatic design methodology was joint to plates of composite materials, and the general solution, a single lap hybrid joint. The main functions, let's say, maximize the bolt load transfer, and here we identified the contact between the bolt shank and the hole. For now, we didn't consider too much a mechanism transfer as in a traditional plate joining by installing a very big preload. So for now we transfer this loading for the bolting towards the contact between the shank and the hole. The second, delay adhesive failure, the second function, and we propose a clamping force, a compression stress. The failure is at the end of the overlap, so we try to take advantage of the clamping force in this region. You will see later. minimize the secondary bending who produce the pure stress. So for that, of course, if there is a bending, we will try to have stiff plates. And finally, we have to find some mechanism to uniformly distribute the load inside the joint. And for this, we are working on in-plane rigidity of the joint. So the zagging now allows to define the second level, third level, if you want, of the functions. So maximize the capacity of bolt, of load transfer. So we have the link between the DPs and the child FRs. Capacity of the bolt transfer through the bearing stress, so the contact between the shank and the hole, and to have this transfer as soon as possible. The DP associated bolt diameter and bolt hole clearance. I think that mechanically is obvious for most of you. We have to have the biggest surface and the minimum clearance to satisfy these FRs. So for the adhesive failure, we have to distribute the compressive stress by the, installed by the clamping force, ensure this compressive stress, and here we have a distributor, let's say generally speaking, a distributor of the stress, and of course the bolt pretension. Minimizing the secondary bending, in fact the flat plates, their thickness has to be increased, and the focus was on minimizing the secondary bending. So the thickness and the position, the offset, that should be minimized. The FR4, so in-plane rigidity of the joint. So we will try to push, let's say, the load path from the edge of the overlap inside the zone between the bolts, and reduce the load transfer near the free edges, of course. This may be achieved by a different adhesive between the bolts and the plate rigidity. So we obtained, after first decomposition, a coupled design. As you may see here, it's an undesired coupling, and how we dealt with. In fact, searching in the literature, doing our test, it showed that we may eliminate the first FR11 because we make a link between this capacity of transfer of the loading and the thickness of the plates by the fact that the bolt diameter generally is the same as the stacking of the two plates. The same diameter has the same dimension as the stacking, the plate stacking. So what we have here, we have an orphan here that we have to move or reformulate. So by reformulation, we can move it a little bit lower and write it in a different manner. So all the FR1 and DP1 will go away. We rewrote everything, and what we may see that this child moved here, and we rewrote also a DP and stiffer and DP 3.1 and 0.2, just to eliminate other couplings that we had in our design metrics. So finally we obtained a decoupled matrix, which is very good for further iteration, that is no longer needed. And finally we had physical integration in a new type of joint that you have here, and we may see some aspects of this new design. The tapered ends to reduce local in-plane stiffness will reduce the peel stress, we installed Belleville type of washers just to expand the effect of the preload near to the edges. A stiffer adhesive between the bolts. Once again, push away the peel stress that can appear here and initiate the failure between the bolts by a stiffer path load, as you can see here. So we compare with the traditional joint, and here we can see that the stiffness is increased. Unfortunately, the bolt transfer is not as good for now. We'll have to continue to work on. We can see that the shear stress distribution, it is now different and at the same level. So there is no improvement, but now is in the middle zone. The peel stress is 30% lower, so this is a very good thing. And we can see also that this stress is more uniformly distributed inside the joint. So, conclusions. We arrived to do a very good decomposition of the new hybrid joint using axiomatic design by having a very good knowledge of what's happened inside this hybrid joint. The physical integration allowed the development of a new type of hybrid joint. The performance was proven when compared to a traditional joint, but the shear stress is the same level, and we have now bolts which are not as loaded as we wanted to. So in the future, we'll continue to work to analyze the effect of ratio of stiffnesses of different adhesive in different zones, optimize the middle zone load sharing between the bolts and the adhesive, and of course continue to find a mechanism to take advantage of the preloading because we know that it's about composite and we cannot squeeze the composite as we can do with a metallic structure. So this is it. Thank you very much.
Thank you very much for the interesting presentation. We do have time for a few questions.
What about the Champlain Bridge and the Jacques Cartier Bridge? Could they use this?
Champlain is going to fall in the
bad condition.
Champlain Bridge. It will fall in the Saint Laurent if we will not change it. So yes, of course, we are interested in every time, as in aeronautic, to do lighter structure and stiffer. So assembly is a problem all over the place. So if there is a failure somewhere, it's on the joining part. So everybody is concerned about methods of assembly. Yes.
Excuse me.
Yeah.
I didn't understood correctly. There was one function that you eliminate.
Yes.
And then you put that function under.
We reformulated slightly this function, and we found that it can have a place under as a child of another parent.
But it doesn't cause any problem because you have one function that goes to another function. So probably in the beginning those function was not independent, or well, I just took that as a possibility.
Yes, yes, we can discuss on this. It was not so easy, but it was a function that was very difficult to write, and maybe there is a point here, but I think that it can be justified in both places and still keep a certain the independence finally of the parents. Yeah.
I think it's an interesting point that Miguel raises, and I liked the way you handled that. And thank you for a very interesting presentation. And we've been doing some work on composite joints as well here, as we're trying to make a bicycle with a bamboo frame, and so it runs into some of the same issues. One question I had though was in regard to a possible application of Axiom 2 and in the washer design that you had to spread the load and and it seems, would that also function to maintain the load, say with change in temperature, because are you accounting for a spring or something?
It's a kind of spring, yeah.
Did you do any analysis on that?
No. It was very interesting because this Belleville type washer can move out the compression zone, but also will give us a larger zone of compression, which is beneficial for the composite. But when temperature is involved, we are not studied this phenomenon.
So it seems like it would reduce the information content and give you a bigger range.
Yes, I think so, yeah.
Very interesting design.
Okay. Thank you.
Do you have any further questions?
Thank you very much.
Thank you again.